Hello everyone. So today, uh, the talk is based on my recent work with Isaac Kim. So briefly speaking, we are starting from a quantum state and propose some entropy conditions on the state, and going from there, we are trying to, yeah, uh, discuss something new about the gap domain wall between two topological ordered fields. Okay, so this is an outline. So I will tell you about our motivation and tell you what is entanglement bootstrap. First, I'll review something for the 2D book, what we were trying to do in that context. And yeah, then we will tell you the story on the gap domain wall, which we think there are some new stuff we want to tell you about. Yeah, finally, there is a summary and outlook. Okay, so yeah, we are all interested in quantum many-body systems, especially with interaction. There's many interesting things can happen. So first we start from a physical system, which is a quantum. There is a Hilbert space which is large. There are a lot of physical degrees of freedom at the microscopic level. And what we want to discuss is the effective theory at large length scales and low energy. Those are the emergent phenomena. So in this talk, the focus will be on 2D gapped system without symmetry. So what with symmetry, usually the thing will make things more interesting, but even without symmetry, yeah, there are a lot of interesting things that can happen. Let's see, concretely in 2D, there's a topological order system. From there, anions can emerge. We don't need symmetry to protect this phenomena because we can add local perturbations. Those phenomena will still exist. One example is the Torrico model, okay, and the emergent law will for anion types and they have non-trivial fusion and braiding, yeah, between them. Okay. So and on the gap domain wall, yeah, let me also introduce gap domain wall because we all discuss this. So when there is a gap domain wall between two topological ordered systems, of course, in the book we still have anions, but there is something new on the boundary. Those excitation alpha on the domain wall is distinct from anions in the book. And anions can fuse onto the domain wall and become a domain wall excitation. Yeah, this is a simple picture. Okay, so what was the, we have anions and the emergent law of anions. Can we come up with a theories to explain this phenomena? We know that a theory is something, theory tries to provide the most logical explanation about why things happen, right? So there's some attempt, yeah, which I'll review. We can, let's see, start from a Lagrangian. That's a approach of a topological quantum field theory. Alternatively, we may start from a Hamiltonian extreme length model. We can start from some good Hamiltonian. From there, we can derive the emergent law of anions. And yeah, what I'm going to tell you about is a different approach which we call entanglement bootstrap. It starts from a quantum state and some local conditions on the entanglement entropy. Start from there, we can derive things. And as is well known in the anion theory, the underlying mathematical theory is expected to be the unitary modular tensor category. More accurately, this is for bosonic system. And we know that yeah, we are somewhat in a somewhat lucky nowadays to have this theory, because this theory is actually being derived from the framework of 2D CFT earlier. And then mathematicians take some time to build this theory. So now we can just use this framework saying, oh, anions may be described by this framework. But in terms of the theory, I mean, the tensor network framework is more like the final answer, but a question remains why this framework works. When do we expect this framework to come up? So a natural question is, maybe can we derive these laws from an assumption on the gap system? So this is a question we want to address. So, okay, now let me first review what is a unitary tensor category in 2D capital phase. So this is a non-concrete conjecture. So that's the statements that the unitary modular tensor category and the chiral central charge classifies 2D bosonic systems, gapped 2D bosonic systems. So what is unitary modular tensor category? So first we need a set of object super selection sectors. Equivalently, those are the anion types. You have the vacuum and antiparticles. You have rules about the fusion. A, B, C are non-negative integers, and they satisfy some additional constraint. From there, we can define the quantum dimension and total quantum dimension. There's a whole a lot of other things which describes the braiding properties. More physically are the S and T, but the things behind those S and T are some gate dependent stuff, but they are important. They are F and R. Furthermore, the S unitary is unitary. That means the braiding statistic is non-trivial. Okay, so this is an example. The detail doesn't matter. What I want to say is, even for a theory with two simple objects, we get a lot of things. So the classification is not trivial. It's very rich. Right. So entanglement bootstrap is an attempt to derive this conjecture, and we tackle this problem from a different viewpoint, and hopefully we can we hope we also discover something new in related physical context, like gap domain wall. So what is it? What is entanglement bootstrap? So here is the setup and the assumption. We start from a 2D quantum state. We call it a reference state, but physically it's the ground state. So we draw some bounded radius disks on the 2D systems and cut it in two different ways. Each of the bounded radius disk, or I should say the radius is bounded, but physically the length scale is larger than the correlation lengths. So for each bounded radius disk, we cut them in two different ways. We propose two entropy conditions. And I should thank my collaborators for tell me this way to cut the system. This is quite insightful, at least from now we know those things are very powerful after we derived things. So S is the entanglement entropy or the von Neumann entropy. Right. So those are the two conditions. The advantage is that we can check the assumptions pretty efficiently once we have a reference state, the quantum state, because the radius are bounded. We don't really need a large system. But I should say this thing is not yet very realistic yet. We need to assume exactly 0 for the moment. Otherwise, the analysis, we expect our analysis to be generalized to approximate case, but that takes a lot more effort. Okay, so let's assume it's exactly 0. Oh, and
question.
Yeah.
So if I think of these entanglement entropies as being, let's say, area law, it doesn't sound natural for these combinations to be 0. Isn't that right? Maybe it is. I see. You're saying that SC is
yes.
essentially just the parameter of C, and I see. Okay. So you would expect this if you had a pure parameter law entanglement.
Right. So yeah, the answer is the following. So C and BC, yeah, each of them is a disk. They have one boundary, so there's one gamma, right? So for B, there's two gamma, so that's why they cancel.
All right. Okay. Good. Thank you.
Yeah. Thanks for the question. Oh, and there is one more assumption I need to say. So we assume that the total Hilbert space is a tensor product of finite dimensional one. This sounds to be a very natural assumption. Many quantum information books just take this assumption as a starting point. But yeah, to us, I want to emphasize this assumption is natural for bosonic systems. For fermionic system, I think a natural generalization is a Z2 graded Hilbert space. So yeah, that's something we need to be a little careful. But yeah, we shall focusing on bosonic systems. All right, so yeah, as Ashwin already clarified, our axiom is actually not very strong in the sense that it is implied by a famous formula for 2D gap system. Yeah, careful people would say this is still a conjecture, but it has been tested numerically on some systems, and people expect this to be pretty general. And right, especially on a system without symmetry. I mean, what condition we can take this sound to be a good starting point? Yeah, in our framework, we can derive, on our way to derive other things, we can derive topological entanglement, which is, something shows the predictive power. So, okay, so yeah, and I should also mention it's pretty easy to generalize this framework to get domain wall and even in higher dimensions. Yeah, it's pretty straightforward actually. Okay, so now let me tell you how entanglement bootstrap works. Now we have a quantum state with area law. So how do we extract the structures? How do we derive anything, right? So we need to have some concept which contains some structure. We find that a useful concept is the information convex set defined on any subsystem omega. So what we do is to first take a thickening of omega. So we thicken it a little bit on its boundary to get subsystem omega prime. On subsystem omega prime, we define a set of density matrices. Each of the density matrices, which we call rho omega prime, is indistinguishable from the ground state on a bounded radius disk. Any bounded radius disk contains in omega prime, okay? So we get a set of density matrices on omega prime. Then we do a partial trace to get the density matrices on omega. The set of such density matrices is an information convex set. Well, this is a somewhat involved definition, but let me tell you the intuition. Why do we do that? So first is the intuition comes from the phenomena of anions. When we create anions, let's say inside the hole, and another maybe the antiparticle outside the annulus, it is known that the we can't detect the anions on any disk-like region because this matrices of the excited state is the same as the ground state. However, we can do a braiding or projective measurement to tell whether there is a non-trivial anion. That means the density matrices on the whole annulus must be different from the ground state. Kind of the information is encoded not in a local way, but somewhat depend on the topology. So that's why it turns out the information convex set is a good thing to characterize those phenomena. Okay, before we derive everything, I would like to say it's a simple, it's easy to see information convex set is a convex set. That means if we take two density matrices, then any combination with a probability p is still in the information convex set. Okay, we will derive the structure of information convex set using the entropy conditions. Yeah, that's our way to derive things. Let me also say the information convex set is the first useful concept. So yeah, start from the condition, entropy condition on the ground state. That's the first non-trivial object we encounter in our theory, but this is not the only one. As the derivation goes on, we will find other useful objects like string operators, but that's, I mean, when we do the logic, those things comes later. So this is the first thing we care about. Any questions so far?
Yeah, actually, go ahead.
Yeah. And so why don't you just use the density matrix of omega while you thicken it? Seems like the density matrix omega already contains the information you want.
Right. Yeah, that's a great question. Yeah, first, indeed, so let's suppose we don't take the actual layer, then we can still try to define a set of density matrices which are locally indistinguishable from the ground state. Yeah, so first for closed manifold, indeed, that's the best way to do it. In that way, we get all the ground states, right? And so the subtlety is the following. Suppose omega is some subsystem with boundaries. Indeed, that set is contains all the useful information, but it also contains some unnecessary information because when the system omega has boundaries, there are the spins on the boundary. It turns out that we can entangle different spins on the boundary in a way that's such that, let's see, this is a spin, this is another, which their set is separated by some large distance, then we can entangle them without change the local reduced density matrices. So it turns out that the ways to entangle them scales with the length of the boundary. So the set will become, very complicated if the boundary is large. But by taking a partial trace, we get rid of those unnecessary information. After that, the set turns out to be topological dependent. So that's why.
Okay.
Yeah, thanks for the question. Any other questions?
Can I just ask, so the set of size omega is obtained by tracing over elements from the slightly larger sets, and then I guess the construction seems kind of recursive. I'm just wondering sort of how it starts. Do you use a particular state for the whole system to start this?
Yeah, so first we need to have a reference state, right? That's our starting point. So yeah, let's see the reference state is a ground state. of some topological order. That's the reference state. Then we find this set on omega prime, but require that this real omega prime to be indistinguishable from the ground state, which is this one. Okay, this is the first step.
Okay, thank you.
Okay, great. You're welcome.
I am still trying to understand this information convex set. So the different elements of the set, what are they labeled by? Are they those, that disk D? Is that what I should be thinking about?
Yeah, okay. Yeah, let me clarify. So the information convex set is labeled by the subsystem omega. And actually, more accurately, it depends on the input reference state psi. Yeah, that's it.
And each element inside that set is what? You have these different density matrices, rho 1, rho 2, that belong to the set, right? These are reduced density matrices on some subregions inside omega prime. Is that how I should think about
it? This one, rho omega prime. You mean?
I mean,
yeah, Ashwin, maybe I can help. So the elements of this set are density matrices on omega, and then they satisfy a certain condition. And that condition is what's given in the second part of the curly brackets there. They're traces of density matrices on this bigger region, omega prime, such that they satisfy this, that they're locally indistinguishable on from the ground state.
Nice. All right. Thanks.
May I also ask a question?
Yeah, sure.
Yeah. So for each omega that you choose, it seems like there's lots of choices of omega prime. Do you also have to label sigma omega with an omega prime? Like, is that an input, or does it end up not mattering?
Oh, yeah, that's a great question. So the question is whether the definition depends on how we choose omega prime. It turns out it doesn't matter as long as omega prime has the same topology as omega. So as long as the thickness is beyond the correlation length, which is the length scale we define in our axioms. Yeah, as long as this is large enough, that doesn't matter, it turns out. Yeah, thanks for the question. This is a very excellent question.
Okay, thank you.
Right, so, okay, hopefully this concept is clear now. So now we are trying to derive some theorems to state, maybe to make it more clear that this is a nice object. The first theorem says if we deform the subsystem in a topological manner by, let's say, taking a partial trace or to get rid of a small disk, do the inverse process, this information convex set is actually isomorphic. It preserves the entropy difference between two extreme points and a distance measures of two density matrices. Okay, I think the picture should be intuitively clear what is going on. And here is a sketch of proof. We use A1 on a local disk. From there, we can show ABC is conditional independent. Then that actually can help to establish a topological sense of deformation. So the topological, that the theory is topological is actually secretly seen from A1. That's the point. And we can also, because those information convex set is not only a convex set, it's a convex set of density matrices. So we can talk more things about density matrices, like what's the correlation, let's say, what's the correlation between this inside and outside, and things like that. It turns out that for extreme point, there's some good statement we can make. here is a statement. So for extreme point on of information convex set of omega prime, so the whole blue region is omega prime, and this formula holds, which implies that there's it's constrained the correlation very strongly, I should say. Yeah, for example, we can derive that those two layers, inner layer and outer layer, has vanishing mutual information. All right, so next we want to start with some structure. So far this is not very much about structure yet. So I'll review how we define super selection sectors in the book, and multiplicity. I'll mention it briefly, and then go to gap domain wall. There's a lot of interesting topic which I don't have time to go through. Okay, but at least, when we want to see how a theoretical framework will better do at least some derivation. So I'll show you one such derivation. That's the Simplex theorem. That tells us how to define the anions, the different anion types. The theorem says if we take annulus X, then the information convex set for X is always a simplex. So a simplex is something with a finite number of extreme points. Those extreme points are orthogonal. We have different labels, and there is a unique vacuum. Our interpretation of anions are the extreme points. So what's the proof? The proof is that X can be divided. Each of them is annulus, so they are isomorphic. We take fidelity as a measure of the overlap of density matrices. Fidelity is conserved. And the second is a general property of fidelity. We take a partial trace, it can only increase. The third is for extreme points. So from there, we can derive that for extreme point, f is smaller than f squared, but f is from 0 to 1. So it can take only either 0 or 1. Okay, so for two extreme point, if f is 0, that means the two extreme points are orthogonal. If f equals to 1, that means the two extreme points are identical. And with the assumption that the Hilbert space is finite dimensional, we can show there is only finite number of extreme points. So that's the Simplex theorem. Okay, and then how about fusion space? How do we get NABC? Right, we can just take a different subsystem, two-hole disk. Let's call it Y. The information convex set is sigma Y. It has a subset which are labeled by A, B, and C. Those extreme point on the annulus shaped subsystems. It turns out each sigma ABC is isomorphic to the other density matrices of finite dimensional Hilbert space. That's why there is a well-defined NABC. Okay. Now we shall go to the gap domain wall. So as we briefly mentioned, on the gap domain wall, there is between two topological alters P and Q, we have anions and excitation on the domain wall. At the physical level, anions can fuse, of course. Anions can breed in the bulk. But the new phenomena is that anions can fuse onto the domain wall excitation, and the domain wall can fuse and other things. So what's the mathematical theory behind those phenomena? there's some recent beautiful works on this object. Here is a reference from the categorical point of view. What I want to say is there's a very nice theory which describes both the fusion and breeding. There's a lot of structure in the category theory. So C is the modular tensor category, C and D, a modular tensor category for the bug. Epsilon is the module category for the domain wall because anions can fuse onto the wall, which kind of some action on the category. Here, what I want to say is, yes, there are good theories, and those theories are on the point excitations. But is the theory of gap domain wall or theory of point excitation, are they the same thing? It turns out we were able to identify something that's kind of not exactly the point excitation because we find some additional super selection sectors which do not correspond to the point excitation directly. So I hope this is something means there's something more to discover about the gap domain wall. So what we do is to start from a very similar set of axioms. So you see these are quite similar. So what's the difference? The difference is that we don't assume the last one. So when BCD is partitioned in this way, we don't use it as an axiom because from general arguments, this can be something else. It may not be zero. Okay. This actually provides some direction on the deformation. That means on the domain wall, we can deform the subsystem in a certain way. So this arc on the domain wall can be deformed into the bug. So we are not sure whether this thing contains only one extreme point. Maybe the information convex set is more interesting. So we did find that it can be something interesting. The proof of the Simplex theorem works for all of those systems. So we can define super selection sector for each of the system. And this N and U subsystem is, to our knowledge, new. So we tried some effort to look for reference and try to interpret our result. So our interpretation is the following. So first we can consider a point sector, point excitation. Of course, this is not local excitation like anions. They should be created by some string operators. Imagine we do a measurement on N and U, and the annulus O. So what do we find? What we find are the one of the super selection sector we define. From this analysis, we can see that each super selection sector on the domain wall actually carries a pair of simpler super selection sector. So there is a theorem, and for that reason we call it parton sectors, and those are in some sense very fundamental because there are a whole lot of super selection sectors in the domain wall. Those are also labeled by those N and U. So that's why we call it parton, because it can use to label different kinds of things. So so this is a story. Due to the time limit, I won't tell you more, but let me briefly mention that we can go a lot further with our framework. Like there's in order to go further, there is an important technique called merging. from merging, the idea is that from some element of information convex set, because of the entropy conditions on the reference state, those conditions actually, in many sense, extend to any element on the information convex set. Due to the conditional independence, we can construct new quantum state from simpler ones. We can change the topology. And in that way, by as you calculate, so we can obtain the density matrices by merging, or we can alternatively obtain density matrices by maximizing the entropy using a more complicated subsystem. In order to get the same results, there is some consistency relation we can derive. Those are very powerful. We can define anti-particles, quantum dimension fusion rules, and derive the topological entanglement by using those analyses. Our framework can, also derive the existence of unitary string operators. We can show that those string operators can deform, the string can deform freely. From there, we can study the breeding statistic. For example, we are able to derive the Verlinda formula, which implies that S is unitary. And we expect to go further from this analysis. So, okay, so here is a summary. Right, so basically we start from a ground state satisfy some entropy conditions. I think the most important thing is we can derive some emergent laws. From there, from those very simple assumptions, and we are actually doing it in a pretty local manner. We are not using the global topology. A byproduct is that the anion data can be extracted locally from many multi-ground states in principle. And so this is the end of my talk. Thank you.
All right, thanks, Bowen, for the very interesting talk. We have a bunch of time, so let's take some questions.
Yeah, I have a question about this convex, density matrix convex, information convex. When you define that, do you have a quasi particle in the middle of a whole? You have a ring, omega is a ring, okay?
Right.
And so when you define this, whether in the middle of this ring, do you have a quasi particle that's just a ground state, nothing there?
Good question. So first, there's let me answer it in the following way. So in terms of I think there's one question is whether we know there is a particle in the ring at this point. A second question is whether we know there is a particle in the ring in the end of the day, right? So let me.
Before that, there's a definition of omega, or sorry, psi. So in the psi is the ground state of this whole square. Is your system is a whole square?
So psi is the ground state of the whole square.
That's already implied there's no quasi particle in the middle.
Right. So right on the state psi, there is no particle in the middle. That's right. Let's take the square. So this square.
Okay.
Is this one? Okay. So there is no quasi particles. And from there we take annulus.
Okay.
Right. Still there is no quasi particle. The way we will find different equilibrium point is that we just look at omega prime and omega by finding, suppose we can find the whole information convex set, then, and suppose this psi is a ground state of topological order, then we should be able to find multiple extreme points. Yeah, in this stage, we still don't have a picture for the excitation yet. That comes later. So later on, we are able to merge the ground state. I see there is a ground state psi. We can merge it with the annulus. So it turns out the complement of the merged state are topologically equivalent to two small holes. Then we can do some analysis and show we can construct an excited state with excitation A. So yeah, then we can claim there is a state with anyons that comes later. But in the end of the day, we know there is such a quantum state with anyons.
I see. But this omega and omega prime, they're always annulus. Is that true? Or omega prime may have a different topology? Seems omega always annulus.
Okay, good question. So here omega can take different topologies.
Omega can take different. So omega is not like a annulus like. Okay.
Right. Annulus is an important topology, but we can take all other topology, any topology we want.
Oh, I see.
And omega prime, we actually didn't. Yeah, in principle, we can take omega prime to be different things also, but in our framework, what we find that what we really want is that omega prime is omega plus an extra layer. We want to keep the topology of them to be the same. So here omega prime has the same topology as omega.
But this convex set is a set where you're changing omega, you're changing omega prime.
Changing omega. Yeah, of course, apparently, so from the definition, we can see it should depend on omega prime, and psi, right?
Yeah.
And as it turns out, we can show that it doesn't depend on omega prime as long as the omega prime is the thickening of omega. So in the end of the day, it is simplified into this.
Okay, so this convex set depend on omega, then this counter, that's for omega with certain topology, we have a counter.
Yeah, yes.
Same point, that's only realized by omega with certain shape or certain topology.
Yeah, it turns out that it only depends on the topology because the set is invariant under smooth deformation. Oh, actually, here I can mention an interesting example. So first, here is the annulus. By the isomorphism theorem, we can deform it, right? Deform it into an annulus over here. That implies that the information convex set of both the annuli are isomorphic. But how about this one? Actually, this non-contractible annulus on the torus may have a different information convex set. And indeed, that happens in some examples.
So my question is the following. In the information context, you say the omega are changing. So maybe some omega is an annulus, some omega is a disk. Do you contain omega which is disk, and where is this when omega is disk?
Oh, okay, great.
What is the point in this information convex? Yeah.
Yeah, if we take omega to be a disk, it turns out we can show that the set contains a unique element. So the unique element is the reference state.
Yeah, but in your it's a simplex. This disk is a point in the simplex. But yeah. In the previous slide.
Yeah, so for disk, we can show it's always a point. The simplex here
is supposed to be a one point in your simplex, right? So where is this point?
Okay, yeah. That actually we use that fact to define the vacuum.
So this vacuum is when x is 6, that is 1, give it counter 1.
Sorry, can I help for a second?
Yeah.
I think Xiaogan is thinking each of these points in the simplex correspond to a different omega. But
Yeah.
that's not, you should think of omega as fixed. It's just an annulus. And each of the points in the simplex is a density matrix on omega. And the idea is that there's a density matrix corresponding to each anion. The anions turn out to be extremal points in this set of density matrices.
Okay, so omega is always annulus, but there's different choice of there's different density matrix which give you this counter. Yeah, I try to understand it.
Oh, I see. Yeah, right. Now I understand your question, Xiaogang. So when we define the anion types, then we always take an annulus shape.
Okay.
When we define some other things, we do need a different topology, like the
Yeah, but let's just do the anion type first. So yeah, so the X always annulus. And so then what is changing here? Now when you say there's a convex, so something is changing.
Yeah, so the density matrices are changing. We are taking different density matrices on the annulus.
But that's confused me. When you have a region X, then you have a density matrix of just a row X as you written down here. So then it looks like a density matrix is fixed by the X. So there's nothing changed. So that's what confused me.
Okay.
Can I ask a question that I think might be related? If you go back to just the slide with the original definition of the information convex set, the row of omega prime, there should be many such ones, right? Because they just have to agree with the ground state on disks of a certain size.
Yes. So yeah,
right?
That's right. Yeah.
Okay, so there's a lot of these row omega primes, and then by tracing them, you create these row of omegas that are the members of this set.
Right. Yeah. Yes. Exactly. Yeah. I think this question helps. So now I can go back to Xiaogang's question. So I think what Xiaogang was thinking about was omega bar. So yeah, in this way, suppose we have a ground state. By taking the partial trace, we get one choice. Yeah, so now why there can be multiple choices, because there can be row omega prime, which are consistent with the ground state on disks, but not globally. So that's why there can be multiple choices.
Oh, I see. So here you actually artificially define the row omega prime, so that they only require they are locally.
Right.
Oh, I see. So yeah. Then that's really correspond to the ground state with the hole in the middle. Then you have all the quasi-particles. Thank you. Yeah, I am confused, but thank you very much.
Yeah, you're very welcome.
Any other questions?
Can I ask a question? I guess we're a little late, but
yeah.
I wondered if you could give an example of parton of a system with non-trivial parton vector or something.
Right. Yeah. Yeah. Right. Excellent. Yeah. Actually, we didn't provide examples in our paper, which is probably. But yeah, here is an example. Yeah. Here I considered a quantum double, so S3, the non-abelian group on both upper and lower half plane. There are the 8 anions in the bulk, right? And so here are the partons. In this model, we find there's for n subsystem, there's 2 choices. We call it A1 and N. Yeah, over here. The quantum dimension is 1 and the square root of 2.
I see.
And those are the point excitations on the domain wall.
Those are the conventionally, wait. So let me ask this. So let's say it was many people may have believed that you could classify domain walls in terms of the properties of the point excitations on the domain walls. Are you saying that knowing the point excitations on the domain walls, does that determine what you call the parton excitations, or is that an additional piece of information that's independent from knowledge of the structure on the domain wall?
That's a good question. At this moment, we don't know. So first, what we do know is that there's some and URET partons, and in principle, we can observe them by, let's say, doing a projective measurement. Your question is on the classification, whether our results imply something about the classification problem. So there are, of course, three possibilities. First, because there is a new observable, maybe the classification can be refined. A second possibility is that it says nothing. In that case, we should be able to derive the property of N and U from the original classification. Of course, the third one is the classification can be reduced in the sense that because there's a new constraint, right? But at this moment, we don't know which is the case.
I see. And one more question. It's only in non-abelian models that you see this. Is that right?
In abelian models, partons can be defined. But I think the most interesting case, let me say, it happens for non-abelian models in the sense that each class can contain multiple excitations. So and U doesn't uniquely fix the sector.
Okay. All right. Thank you.
Yeah, you're welcome.
Okay, if there's no more questions, then this is a good time to end. Thank you again very much, Bowen.
Yeah, thanks.